At 0100 hours on November 15, 1942, USS Washington's radar team observed a large echo appear on their SG surface search radar display, range 8,400 yards, bearing 330 degrees. The contact was a battleship. She was moving slowly through iron. Bottom sound, unaware that American guns were already tracking her through the night. For American destroyers were sinking or aflame. USS South Dakota, the other battleship in Task Force 64, had been heavily damaged by Japanese fire after electrical failures crippled her systems. Japanese searchlights swept the sea, hunting for more targets, but they never located USS Washington. The Japanese battleship Kirishima had no radar. Her lookouts strained to see through complete darkness. Her optical rangefinders were useless without illumination. Her fire control teams had no idea an American battleship was less than 5 miles away, its guns already trained on their ship, waiting only for the order to open fire. On Washington's bridge, Rear Admiral Willis Augustus Lee stood beside Captain Glenn Benson Davis. Lee had been tracking the Japanese formation on radar for nearly 20 minutes. He knew precisely where every enemy vessel was located. The Japanese knew nothing. Lee had spent years preparing for a moment like this. He understood radar better than any senior officer in the U.S. Navy. Now he would demonstrate that electronics could defeat experience, doctrine, and numerical superiority. What occurred during the next 7 minutes would alter naval combat forever. Night surface warfare in 1942 was dominated by the Imperial Japanese Navy. For more than 20 years, the Japanese had refined tactics that made the darkness their greatest ally. Rigorous training in low-light conditions, superior optical equipment, and an aggressive doctrine focused on rapid torpedo strikes and close-quarters gunnery. Japanese destroyer crews drilled until they could fight without seeing. Their commanders understood a crucial truth: darkness nullified American advantages in firepower and industrial output. This doctrine had produced devastating results. In August 1942, at the Battle of Savo Island, Japanese cruisers surprised an Allied force and sank 4 heavy cruisers. In 32 minutes. American ships possessed early radar, but captains did not trust the technology. By the time lookouts confirmed visual contacts, Japanese long-lance torpedoes were already on the way. The battle became a textbook example of failure to use radar effectively. USS Chicago had SC air search radar. The operator detected contacts at 43,000 yards. But the information reached the bridge far too slowly. By the time the captain was notified, Japanese ships were already visible. The radar warning provided no advantage. USS Ralph Talbot, acting as a radar picket, detected Japanese vessels but misidentified them as friendly. The formation commander doubted the radar report and failed to order battle stations. The Japanese achieved total surprise despite being detected miles in advance. In October at Cape Esperance, American forces achieved surprise using radar, but then lost cohesion when the formation maneuvered into disarray. Rear Admiral Norman Scott had arranged his cruisers and destroyers in column. When radar detected the Japanese, he attempted to cross the T, a classic advantage. But in darkness, with ships turning independently, the formation unraveled. Vessels fired at contacts without knowing whether they were friend or foe. USS Duncan engaged what she believed were Japanese ships, some were American. Duncan was struck by friendly shells, then by enemy fire, and sank. USS Boise was illuminated by Japanese searchlights and took multiple hits before support arrived. Though the Americans won tactically, sinking a Japanese heavy cruiser and destroyer, the battle exposed how easily radar advantages could be wasted through poor coordination. On November 13, the opening phase of the naval battle of Guadalcanal became a close-range melee. American cruisers and destroyers fought Japanese battleships at ranges under 3,000 yards. Ships fired at muzzle flashes. Searchlights blinded gun crews. USS Atlanta took 19 shell hits and a torpedo. USS Juno limped away, damaged, only to be torpedoed and sunk by a submarine hours later. Rear Admiral Daniel Callahan and Rear Admiral Norman Scott were both killed, the only two American admirals to die in surface combat during the entire Pacific War. The Americans halted the Japanese bombardment of Henderson Field, but at terrible cost. 4 destroyers sunk, 2 light cruisers lost, numerous ships crippled, and more than 700 American sailors killed. It was a tactical victory that came at a price the fleet could not afford. The cruiser force was shattered. Most surviving ships needed repairs. Henderson Field had been saved for one more night, but the Japanese were returning. Japan lost Battleship High, crippled during the battle and finished by aircraft on November 13, along with 2 destroyers, but they were preparing another major attempt. Vice Admiral Nobutake Kondo was bringing Battleship Kirishima south with cruisers and destroyers to bombard Henderson Field on the night of November 14. If the airfield were destroyed, Japanese troops could land freely and retake Guadalcanal. The strategic situation was dire. Guadalcanal was the first major American offensive in the Pacific. If it failed, the entire island-hopping strategy would be discredited. The Marines on Guadalcanal were exhausted, 3 months of constant fighting, poor supplies, and relentless Japanese attacks. Henderson Field was their lifeline. Aircraft from the airfield protected supply convoys and struck at Japanese reinforcements. Without it, the Marines could not hold. Admiral William Halsey had almost nothing left to stop Kondo's bombardment group. The cruiser force was wrecked. He had one functioning aircraft carrier, USS Enterprise. But carrier planes could not fight at night. His only option was to strip Enterprise of her battleship escorts and send them into Iron Bottom Sound for another night fight. It was a calculated gamble. If the battleships were sunk, Enterprise would be exposed. But if Henderson Field fell, Guadalcanal would be lost regardless. The problem was that night combat favored the Japanese. American ships had better radar than they had possessed at Savo Island or Cape Esperance, but radar alone had not prevented disaster. The technology had to be used properly, integrated into tactics and command decisions. Most American admirals in 1942 still regarded radar as a promising experimental device, not a decisive weapon. They had been trained in an era when visual spotting and optical rangefinding were the only way to fight. Radar challenged decades of doctrine. Many commanders hesitated to rely on it completely. Admiral Willis Lee was different. Lee understood radar because he had studied it. He worked with engineers designing fire control systems. He reviewed British reports on radar-directed gunnery. He trained his crews to fight with radar as their primary sensor. Where others said radar was unproven, Lee insisted it would decide the struggle for the Pacific. Willis Augustus Lee was 54 in November 1942. Born in Kentucky in 1888, he graduated from the Naval Academy in 1908. His strength was not in traditional seamanship. Lee was a marksman. At the 1920 Antwerp Olympics, he won 7 shooting medals, 5 gold, 1 silver, 1 bronze. He was the most successful athlete at those games. His record stood for 60 years, until it was tied in 1980. His specialty was long-range rifle shooting, where tiny changes in wind, temperature, and distance determined success or failure. Lee understood that hitting a target at range required exact measurement. Minor errors grew with distance. Wind drift had to be computed. Temperature altered powder burn rates. Air pressure influenced bullet trajectory. Lee mastered measuring these factors and incorporating them into his shooting. Lee understood precision. He viewed battleship guns as tools that required the same attention to variables as rifle marksmanship: range, speed, wind, ship motion, shell ballistics. Every factor had to be calculated accurately. For decades, navies relied on optical rangefinders and visual spotting for this data. Lee recognized that radar could provide far better information, and with unmatched accuracy. Optical rangefinders measured range by comparing images from two lenses separated by several meters. The operator adjusted the images until they aligned, then read range from a scale. The process required good visibility, steady hands, and practice. Accuracy was typically 1% of range at best. At 10,000 Y, the error could be 100 yard or more. In darkness or poor visibility, optical rangefinders were nearly useless. Radar measured range by timing radio wave reflections. Radio waves traveled at the speed of light. The radar transmitted a pulse, measured how long until the echo returned, and calculated range from the time delay. The measurement was electronic, instantaneous, and unaffected by darkness, smoke, or weather. The Mark III fire control radar on Washington could measure range to within 40 yard plus 0.1% of range. At 10,000 yards, the error was less than 54 yards. This was twice as accurate as optical rangefinders in daylight and infinitely better than optical rangefinders at night. Between the wars, Lee served as director of fleet training at the Office of the Chief of Naval Operations. He worked on gunnery development and fire control systems. When radar technology emerged in the late 1930s, Lee immediately understood its implications. Radar could measure range more accurately than optical rangefinders. Radar could track targets in darkness, fog, or smoke. Radar could see over the horizon. If properly integrated with fire control computers, radar could revolutionize naval gunnery. Lee pushed for radar development and integration into fleet operations. He studied British reports on radar use in the Atlantic. He attended technical briefings on radar equipment. He visited research facilities developing radar systems. By the time radar-equipped ships began deploying to the fleet in 1941 and 42, Lee probably understood radar capabilities better than anyone at flag rank. Lee was given command of Battleship Division 6 in August 1942. The division consisted of two new North Carolina-class battleships, USS Washington and USS South Dakota. Both ships carried 9 16-inch guns in 3 triple turrets. Both had advanced radar systems. Both were fast, capable of 28 knots. Lee made Washington his flagship and immediately began training his crews in radar-directed gunnery. Lee's approach was radical. Traditional doctrine said radar was a backup to visual systems. Use radar to find targets, then switch to optical control for firing. Lee made radar the primary sensor. He reorganized Washington's fire control procedures. So, radar operators worked directly with the gun directors and plotting rooms. Information flowed from radar to fire control without going through layers of bridge officers who might question or delay the data. Lee drilled his crews constantly. Track targets on radar. Calculate firing solutions from radar data. Fire without visual confirmation. Trust the electronics. USS Washington fired her main battery at night twice in January 1942 during training exercises in Casco Bay, Maine. Both times the gunnery was directed entirely by radar. No visual sighting of the targets, no optical range finding, just radar providing data to the fire control computer. The results convinced Lee that radar could control accurate fire at ranges where visual spotting was impossible. Washington's shells landed close enough to the target sleds that Lee knew the system worked, but convincing the Navy required proving it in combat against a shooting enemy. Training exercises were one thing. Combat with ships maneuvering and shooting back was entirely different. The test came on November 14, 1942. Intelligence reports indicated Vice Admiral Nute Kondo was bringing a bombardment force to Guadalcanal. The force included battleship Kirishima, heavy cruisers Otago and Takao, light cruisers Sai and Nagara, and 9 destroyers. Their mission was to destroy Henderson Field and land reinforcements. The Japanese had tried this twice in the previous 2 nights and been turned back both times. Now they were coming with overwhelming force. Wholly ordered Lee to take Task Force 64 and stop them. Lee had USS Washington, USS South Dakota, and 4 destroyers, USS Walk, USS Benham, USS Preston, and USS Gwynn. It was everything available. Most other American warships in the area were damaged or low on fuel or ammunition. Lee knew the odds. 6 ships against 1 battleship, 4 cruisers, and 9 destroyers. The Japanese had overwhelming numerical superiority. They had more guns. They had more torpedoes. They had better night fighting experience. They had the tactical initiative because they knew where they were going and when they needed to arrive. Lee would have to intercept them in waters the Japanese knew intimately. Lee's only advantage was radar. He intended to use it completely. His plan was simple. Position his force to intercept the Japanese as they approached Guadalcanal. Use the destroyers as a screen to deal with Japanese destroyers and absorb the initial torpedo attacks. Keep the battleships back in darkness where Japanese visual spotting couldn't find them. Use radar to track Japanese capital ships. Wait until the range was right, then open fire with radar-directed salvos. The plan required perfect radar performance, perfect fire control calculations, and enough luck to avoid being hit by torpedoes or found by Japanese searchlights. Lee accepted these risks because any other approach meant fighting on Japanese terms, and fighting on Japanese terms meant losing. Task Force 64 approached Guadalcanal from the south on the afternoon of November 14, Japanese reconnaissance aircraft spotted the formation and reported the sighting. The Japanese identified the force as 1 battleship, 1 cruiser, and 4 destroyers. The identification was wrong, but close enough to alert Kondo that American ships were in the area. Both sides knew a battle was coming. The question was who would gain advantage when the fighting started. At 2,300 hours, Lee's force rounded the western tip of Guadalcanal and headed north into Iron Bottom Sound. The passage between Guadalcanal and Savo Island was about 8 miles wide. It was a confined space for battleship operations. Maneuvering room was limited. The water was filled with wrecks from previous battles. Survivors from earlier engagements were still in the water on rafts. The tactical situation was as bad as it could be for capital ships. But Lee had no choice. If he stayed outside the Sound, the Japanese would bombard Henderson Field unopposed. He had to engage them here. The night was dark. No moon. Low clouds blocked starlight. Visibility was less than 1 mile. The sea was calm with a light chop. The air was hot and humid. Temperature was about 85 degrees. The smell of jungle vegetation drifted across the water from Guadalcanal. Occasional lightning flashed in distant thunderstorms. It was perfect weather for radar and terrible weather for visual spotting. Washington's SG radar began picking up contacts beyond Savo Island at 2,305 hours. Multiple groups of ships moving south. Lee watched the radar plot display. He counted contacts. More than a dozen vessels in 3 groups. The Japanese bombardment force was approaching on schedule. Lee positioned his destroyers in line ahead of the 2 battleships. Walker, Benham, Preston, Gwynn. The destroyers would screen against torpedo attacks and engage enemy destroyers. The battleships would hang back and use their radar advantage to engage the larger enemy units from distance. Lee sent a message over the TBS radio to all ships. "This is Lee. We're going into a big fight. Keep your heads. Stay alert. Trust your instruments." The technology that gave Washington her advantage had a remarkable history. Radar development in the United States began in the 1930s, but early systems were primitive. The breakthrough came from Britain. In September 1940, a British technical mission arrived in the United States, carrying a black box containing the cavity magnetron. This device could generate microwave frequency radio waves at power levels useful for radar. British scientists had invented it at Birmingham University. They shared the technology with America in exchange for American industrial capacity to mass-produce radar systems. The Radiation Laboratory at the Massachusetts Institute of Technology received the magnetron in November 1940. Within months, engineers developed the first microwave radar prototypes. The SG surface search radar emerged from this work. It operated at approximately 3,000 megahertz using 10 centimeters wavelength. This was revolutionary. Earlier radars used wavelengths measured in meters. The SC air search radar that many ships carried operated at 200 MHz with a wavelength of 1.5 m. The shorter wavelength of the SG provided much better resolution. Contacts appeared as distinct points rather than fuzzy blobs. The SG had another innovation, the plan position indicator display. Previous radars showed returns as spikes on an oscilloscope. The operator watched a horizontal line sweep across the screen. When the radar pulse hit something, a spike appeared on the line. The operator had to interpret the spike height and position to determine bearing and range. It required training and concentration. The PPI display was completely different. It was a circular screen 9 in diameter showing a map-like view. Washington appeared at the center as a bright dot. North was at the top. Contacts appeared as bright points of light at their actual bearing range. Relative to Washington, the display updated continuously as the antenna rotated at 15 revolutions per minute. Operator could see the entire tactical situation at a glance. Formation positions were obvious. Contact courses could be determined by watching how the points moved. Multiple contacts were easy to track. It was intuitive and required less training than the oscilloscope displays. USS Augusta received the first operational SG radar in April 1942. Washington received hers during her August 1942 refit at Philadelphia Navy Yard. By November, fewer than 50 American warships had SG radar. It was still cutting-edge technology. Many officers viewed it skeptically. The equipment was complex and could malfunction. The vacuum tubes failed regularly and had to be replaced. The antenna motors sometimes jammed. In rough seas, the mast head motion could affect the antenna position. Officers who'd served their entire careers without radar weren't convinced it was worth depending on. The SG antenna was mounted on the forward face of Washington's main tower structure. The antenna was a rectangular frame about 2 feet by 3 feet containing the transmitter and receiver. It rotated continuously, scanning 360 degrees. The mounting position on the forward tower gave excellent forward and side coverage, but created a blind sector to the rear. Contacts directly astern might not be detected. Lee accepted this limitation because most contacts would be ahead of Washington as she advanced into the engagement area. Maximum range on battleship-sized targets was approximately 30 miles in good conditions. Smaller ships like destroyers could be detected at 15 to 18 miles. Light cruisers appeared at around 20 m. The bearing accuracy was within 1 degree. Range accuracy was within 100 yards at maximum range, improving to within 50 yards at closer ranges. These were impressive specifications, but the real advantage was that radar worked in complete darkness. Visual lookouts were limited to a mile or less in these conditions. Radar could see 6 to 8 times farther. Washington also carried Mark III fire control radar on her main battery directors. 2 Mark 38 directors controlled the main battery. One director was mounted on top of the forward tower structure. The second was mounted on a tower aft of the second funnel. Each director had a Mark III radar antenna mounted directly on it. The Mark III operated at a different frequency than the SG, approximately 100 MHz. It was specifically designed for gun laying, not search. The antenna was smaller and focused its energy in a narrow beam. This gave precise ranging, but covered only the area where the director was pointed. The Mark III measured range with exceptional accuracy. Within 40 yard plus 0.1% of the range. At 8,000 Y the total error was less than 50 yard. At 15,000 Y the error was about 190 Y. This was far better than optical rangefinders. Navy optical rangefinders were typically 26 feet long, using the maximum separation possible on a ship. In ideal daylight conditions with a clear target, a skilled operator might achieve 1% ranging accuracy. At 10,000 yard, that meant errors of 100 yard. At night with a dark target, errors could be several hundred yard. Many times the optical rangefinder simply couldn't get a reading at all. The Mark III radar worked in any visibility conditions and provided consistent, accurate ranging. The Mark III fed range data to the Mark VIII Rangekeeper, an analog mechanical computer weighing several tons. The Rangekeeper was installed in the plotting room below the armored deck. It was essentially a room-sized calculator built from gears, cams, and servo motors. The machine was about 12 feet long, 6 feet wide, and 7 foot tall. It required 3 operators to input data and monitor its operation. The Rangekeeper accepted inputs for own ship course and speed, target bearing, target range, target course, target speed, wind direction, wind speed, air temperature, and dozens of other variables affecting shell trajectory. From these inputs, it calculated where to point the guns. So, shells fired now would intersect with the target's future position when they arrived. The calculation had to account for shell flight time, typically 20 to 30 seconds. During that time, both Washington and the target would move. The shells would follow a ballistic arc affected by wind, air density, and the Earth's rotation. All these factors had to be continuously recalculated. The Rangekeeper updated continuously as radar provided new range data every few seconds. The computer recalculated as Washington maneuvered. The computer compensated for the change in bearing and relative motion. The gun orders went electronically to the turrets where motors trained the guns in bearing and elevated the barrels. The entire process, from radar measurement to gun pointing, took seconds. Human rangefinder operators and manual calculators needed minutes to achieve the same result, assuming they could see the target at all. The system worked when properly integrated, but it had limitations that Lee understood perfectly. The Mark III radar couldn't distinguish shell splashes from the target return. During daylight gunnery, spotters in the directors watched where shells landed through optical instruments. They called corrections up, down, left, right. The rangekeeper adjusted the solution and the next salvo landed closer. This process of firing and spotting produced accurate shooting within a few salvos. In darkness, spotting was impossible. Washington would fire calculated salvos without being able to observe where they landed. The only feedback would be if shells hit and started fires visible to lookouts. Otherwise, Lee would simply trust that the radar ranging was accurate and the fire control solution was correct. This was the gamble. Lee was betting everything on electronics that had never been fully tested in combat this way. If the radar lost track of the target, the guns would fire at empty ocean. If the fire control computer made an error in the calculations, shells would miss by hundreds of yards. If Japanese ships maneuvered unpredictably, the solutions would be wrong by the time the shells arrived. If the radar data was slightly off, the entire firing solution would be degraded. Lee accepted these risks because fighting without radar meant certain blindness. Fighting with radar meant at least having a chance to see and shoot first. In night combat, shooting first usually meant winning. At 2,317 hours, Washington's SG radar detected multiple contacts emerging from behind Savo Island, range 18,000 yards. The contacts were moving south in two groups. Lee ordered his formation to battle stations. General quarters had already been set hours earlier, but Lee's message emphasized that contact was imminent. The four destroyers were arrayed in column ahead of the battleships. Walker leading, then Benham, Preston, and Gwynn. The destroyers were spaced about 600 yards apart. Washington followed about 2,000 yards behind Gwynn. South Dakota was supposed to follow Washington by another 2,000 yards, but Captain Gatt maneuvered independently, and South Dakota's position varied throughout the engagement. Commander Thomas Fraser on Walker had the most advanced radar in the destroyer force. His SG radar, similar to Washington's, picked up the Japanese destroyer screen at 12,000 yards. Fraser was an experienced destroyer commander who understood radar capabilities. He recognized the contacts as enemy destroyers and reported to Lee. Fraser requested permission to launch torpedoes at the torpos contacts. Destroyers carried 10 torpedoes in two quintuple mounts. Launching early would allow the torpedoes to run toward the enemy formation. Some might hit more. Importantly, Japanese ships detecting incoming torpedoes would maneuver to avoid them, disrupting their formation. But the torpedo hit forward of the main watertight bulkhead. The bulkhead held. Water rushed in through the destroyed bow section, but stopped at the bulkhead. Benham's stern section from the bridge aft remained intact and watertight. Taylor managed to stabilize the ship. The engines still worked. Steering was functional using the rudder, but Benham could only make 5 knots with her bow gone. The water resistance was too great. She was out of the fight. Taylor withdrew south toward Guadalcanal, hoping to beach the ship for emergency repairs. Remarkably, Benham stayed afloat all day November 15. She attempted to reach Guadalcanal, but couldn't make headway. Finally, at 1938 hours, after nearly 20 hours afloat with her bow missing. Benham was scuttled by gunfire from USS Gwin. All crew members survived. Nobody was killed by the torpedo hit. It was the only good news from the destroyer engagement. Gwin was fourth and last in line. Lieutenant Commander John Fellows saw 3 to lead destroyers hit ahead. Explosions and fires indicated the destroyer screen was being overwhelmed. Fellows ordered Gwin to engage with all guns and prepare to maneuver independently. Gwin's 5 inches battery fired at multiple Japanese targets. At 2,332 hours, a Japanese shell hit Gwin's after engine room. The explosion killed several men in the engineering spaces and disabled one engine, but Gwin remained operational on her remaining engine. She could still make about 20 knots. Fellows continued engaging until Lee ordered the surviving destroyers to withdraw at 0045 hours. In 15 minutes, the American destroyer screen had been effectively destroyed. 2 destroyers sunk with heavy loss of life. 1 crippled and withdrawing with her bow blown off, 1 damaged, but still operational. The Japanese destroyer and cruiser screen had executed their night combat doctrine perfectly. They'd engaged aggressively with torpedoes and gunfire. They'd overwhelmed the American destroyers with concentrated fire. They'd broken through the screening force and cleared the way for Kirishima and the heavy cruisers to engage the American battleships. This was exactly what Japanese destroyer doctrine called for. Destroy the screening units, then allow the capital ships to engage the enemy battle line. This was exactly the scenario Lee had feared but accepted as unavoidable. His destroyers couldn't match Japanese destroyers in night combat. The Japanese had better torpedoes, better training, better tactics, and more experience. But Lee had positioned his destroyers to absorb the initial attack and protect the battleships. The destroyers had done their job at terrible cost. Now it was up to Washington and South Dakota to complete the mission. Everything depended on the battleships using their radar advantage before the Japanese found them. USS South Dakota had maneuvered independently when the destroyer action started. Captain Thomas Gatch was an aggressive officer who wanted to close with the enemy. He moved South Dakota ahead of Washington to engage. At 2,338 hours, South Dakota's SC air search radar picked up surface contacts at 18,000 yards. The SC radar was less capable than the SG, but it could detect large ships at long range. Gatch ordered his main battery to prepare to engage. The gun crews loaded armor-piercing shells. The fire control team began tracking the contacts. South Dakota was preparing to fire when disaster struck. South Dakota's electrical system failed. The failure was caused by human error compounded by poor design. During the afternoon, electrical repairs were being conducted. A circuit breaker tripped. The chief engineer manually reset the breaker while it was still under load. Navy regulations prohibited this because it could cause cascading failures. That's exactly what happened. Resetting the breaker under load caused it to trip again. When it tripped, caused other breakers in the circuit to trip. The failures cascaded through the electrical distribution system. Within seconds, the entire ship lost power. Everything went dark. Radar screens went black. Gun directors lost power. Fire control computers shut down. Communications went dead. Ventilation stopped. Even emergency lighting failed in some compartments. Damage control teams worked frantically in complete darkness trying to restore power. They had flashlights and battle lanterns, but resetting breakers and troubleshooting electrical systems in darkness was nearly impossible. The engineering crew managed to restore partial power within about 5 minutes, but the damage was done. South Dakota's combat capability was shattered at the worst possible moment. Without radar, South Dakota was blind. Her lookouts could see the burning American destroyers astern, but they couldn't see Japanese ships ahead. Without fire control power, her main battery couldn't be aimed. Without communications, Captain Gat couldn't coordinate with Lee or with his own gun crews. South Dakota continued moving forward on momentum and manual steering. She was heading directly toward the Japanese force without sensors or working weapons. It was a nightmare scenario. At 0001 hours, power was partially restored. Some radar systems came back online. Fire control systems rebooted, but the ship had drifted during the power failure. South Dakota had sailed to within 5,000 yards of the Japanese force, far closer than Gat intended. Japanese cruiser Retargo detected the American battleship at close range and illuminated her with a searchlight. The powerful beam found South Dakota immediately. She was perfectly silhouetted by the burning American destroyers behind her, backlit by the fires. Every Japanese ship in range opened fire. Kirishima fired her main battery of 14-inch guns at a range of 5,500 yards. This was point-blank range for battleship guns. The Japanese shells crossed the distance in about 8 seconds. Heavy cruisers Atarago and Takao fired their 8-inch guns. Light cruiser Sendai fired 6-inch guns. Multiple destroyers fired 5-inch guns. South Dakota was hit by shells of every caliber. The ship was struck at least 27 times in 3 minutes. Most hits came from 8-in, 6-in, and 5-inch guns. These shells couldn't penetrate South Dakota's armored belt or turret faces, but they destroyed everything topside. The forward main battery director took a direct hit from a 14-inch shell. But the torpedo hit forward of the main watertight bulkhead. The bulkhead held. Water rushed in through the destroyed bow section, but stopped at the bulkhead. Benham's stern section from the bridge aft remained intact and watertight. Taylor managed to stabilize the ship. The engines still worked. Steering was functional using the rudder, but Benham could only make 5 knots with her bow gone. The water resistance was too great. She was out of the fight. Taylor withdrew south toward Guadalcanal, hoping to beach the ship for emergency repairs. Remarkably, Benham stayed afloat all day November 15. She attempted to reach Guadalcanal, but couldn't make headway. Finally, at 1938 hours, after nearly 20 hours afloat with her bow missing, Benham was scuttled by gunfire from USS Gwin. All crew members survived. Nobody was killed by the torpedo hit. It was the only good news from the destroyer engagement. Gwin was fourth and last in line. Lieutenant Commander John Fellows saw 3 to lead destroyers hit ahead. Explosions and fires indicated the destroyer screen was being overwhelmed. Fellows ordered Gwin to engage with all guns and prepare to maneuver independently. Gwin's 5-inch battery fired at multiple Japanese targets. At 2,332 hours, a Japanese shell hit Gwin's after engine room. The explosion killed several men in the engineering spaces and disabled one engine, but Gwin remained operational on her remaining engine. She could still make about 20 knots. Fellows continued engaging until Lee ordered the surviving destroyers to withdraw at 0045 hours. In 15 minutes, the American destroyer screen had been effectively destroyed. 2 destroyers sunk with heavy loss of life. 1 crippled and withdrawing with her bow blown off, 1 damaged, but still operational. The Japanese destroyer and cruiser screen had executed their night combat doctrine perfectly. They'd engaged aggressively with torpedoes and gunfire. They'd overwhelmed the American destroyers with concentrated fire. They'd broken through the screening force and cleared the way for Kirishima and the heavy cruisers to engage the American battleships. This was exactly what Japanese destroyer doctrine called for. Destroy the screening units, then allow the capital ships to engage the enemy battle line. This was exactly the scenario Lee had feared but accepted as unavoidable. His destroyers couldn't match Japanese destroyers in night combat. The Japanese had better torpedoes, better training, better tactics, and more experience. But Lee had positioned his destroyers to absorb the initial attack and protect the battleships. The destroyers had done their job at terrible cost. Now it was up to Washington and South Dakota to complete the mission. Everything depended on the battleships using their radar advantage before the Japanese found them. USS South Dakota had maneuvered independently when the destroyer action started. Captain Thomas Gatch was an aggressive officer who wanted to close with the enemy. He moved South Dakota ahead of Washington to engage. At 2,338 hours, South Dakota's SC air search radar picked up surface contacts at 18,000 yards. The SC radar was less capable than the SG, but it could detect large ships at long range. Gatch ordered his main battery to prepare to engage. The gun crews loaded armor-piercing shells. The fire control team began tracking the contacts. South Dakota was preparing to fire when disaster struck. South Dakota's electrical system failed. The failure was caused by human error compounded by poor design. During the afternoon, electrical repairs were being conducted. A circuit breaker tripped. The chief engineer manually reset the breaker while it was still under load. Navy regulations prohibited this because it could cause cascading failures. That's exactly what happened. Resetting the breaker under load caused it to trip again. When it tripped, caused other breakers in the circuit to trip. The failures cascaded through the electrical distribution system. Within seconds, the entire ship lost power. Everything went dark. Radar screens went black. Gun directors lost power. Fire control computers shut down. Communications went dead. Ventilation stopped. Even emergency lighting failed in some compartments. Damage control teams worked frantically in complete darkness trying to restore power. They had flashlights and battle lanterns, but resetting breakers and troubleshooting electrical systems in darkness was nearly impossible. The engineering crew managed to restore partial power within about 5 minutes, but the damage was done. South Dakota's combat capability was shattered at the worst possible moment. Without radar, South Dakota was blind. Her lookouts could see the burning American destroyers astern, but they couldn't see Japanese ships ahead. Without fire control power, her main battery couldn't be aimed. Without communications, Captain Gat couldn't coordinate with Lee or with his own gun crews. South Dakota continued moving forward on momentum and manual steering. She was heading directly toward the Japanese force without sensors or working weapons. It was a nightmare scenario. At 0001 hours, power was partially restored. Some radar systems came back online. Fire control systems rebooted, but the ship had drifted during the power failure. South Dakota had sailed to within 5,000 yards of the Japanese force, far closer than Gat intended. Japanese cruiser Otago detected the American battleship at close range and illuminated her with a searchlight. The powerful beam found South Dakota immediately. she was perfectly silhouetted by the burning American destroyers behind her, backlit by the fires. Every Japanese ship in range opened fire. Kirishima fired her main battery of 14-inch guns at a range of 5,500 yards. This was point-blank range for battleship guns. The Japanese shells crossed the distance in about 8 seconds. Heavy cruisers Atarago and Takao fired their 8-inch guns. Light cruiser Sendai fired 6-inch guns. Multiple destroyers fired 5-inch guns. South Dakota was hit by shells of every caliber. The ship was struck at least 27 times in 3 minutes. Most hits came from 8-in, 6-in, and 5-inch guns. These shells couldn't penetrate South Dakota's armored belt or turret faces, but they destroyed everything topside. The forward main battery director took a direct hit from a 14-inch shell. The shell didn't penetrate the armored director, but the impact destroyed the optics and knocked out the crew inside. Men were killed by concussion even though the shell didn't explode. The radar antennas were shattered by shell fragments. Gun mounts were hit. The number 3 turret took an 8-inch shell hit on the barbette, but the shell didn't penetrate. Fires started in multiple locations. The superstructure was riddled with holes. 39 men were killed. 59 were wounded. The ship looked like she'd been through a scrap metal shredder. South Dakota's armor did its job. None of the hits penetrated vital spaces. The engines kept running. The ship maintained speed. The main battery turrets could still fire in local control without the directors. But South Dakota was effectively out of the fight. She couldn't use radar. She couldn't use centralized fire control. She was partially blind and heavily damaged. Captain Gatt ordered an emergency turn to starboard to escape the Japanese formation. South Dakota turned hard and disappeared back into darkness, heading south away from the enemy. Her sacrifice had achieved one critical result. She'd drawn every Japanese ship's attention. While South Dakota was being pounded, USS Washington was invisible in the darkness, tracking Japanese ships on radar, preparing to fire. The Japanese thought they'd won. In less than 20 minutes, they'd destroyed or driven off every American ship they'd engaged. 4 destroyers sunk or crippled. 1 battleship damaged and retreating. Admiral Kondo on cruiser Atarago congratulated his force on their success. He ordered the formation to reform and proceed north to bombard Henderson Field. The primary mission could now proceed unopposed. Japanese commanders didn't know that USS Washington existed. Every Japanese ship had been focused on the destroyers and South Dakota. Washington had stayed back in darkness, tracking everything on radar, waiting for the perfect moment. In Washington's plotting rooms and directors, the radar operators and fire control teams had complete information. The SG radar showed all Japanese ship positions clearly. The returns were distinct and easy to track. The Mark III fire control radar on the forward director was locked onto the largest contact, tracking it continuously. The radar measured range every few seconds. The Mark VIII rangekeeper computed the firing solution, continuously updating as both ships moved. Target bearing, target range, target course and speed estimated from radar plot tracking. Own ship course and speed. Wind, all the variables fed into the computer. The solution was ready. All turrets were loaded with armor-piercing shells. The guns were trained on target and elevated to the calculated angle. Everything was ready. Washington just needed permission to fire. Admiral Lee stood on the bridge with Captain Davis. Lee wore a headset connected to the radar plot and fire control circuits. He could hear everything the operators were saying. He watched the radar plot display showing the tactical situation. He could see the Japanese battleship clearly on the screen. Range 8,400 yards. The target was moving slowly northwest heading toward Henderson Field. The Japanese ship had no idea Washington existed. Lee had the perfect setup. His ship was invisible. His target was fully illuminated on radar. His guns were ready. This was the moment everything had been building toward. Lee looked at Captain Davis and said simply, "Stand by, Glenn." "Here they come." Davis gave the order that changed everything. "Main battery commence firing." At 0100 hours. Exactly 1 o'clock in the morning of November 15, 1942. USS Washington opened fire. All 9 16-inch guns and 3 triple turrets fired together in a single massive salvo. The sound was indescribable. The blast pressure was so intense it could rupture eardrums. The muzzle flash lit up the entire sky like lightning. The ship shuddered and heeled slightly to starboard from the recoil force. 9 shells weighing 2,700 pounds each flew toward Hiroshima at 2,600 foot-pers. That's about 1,800 miles per hour. The shells were in the air for approximately 20 seconds while they covered 8,400 yards. Each shell was a Zaire, an armor-piercing projectile. The shell body was forged steel. The nose was hardened to penetrate armor. Inside was about 40 pounds of high explosive with a base detonating fuse. The fuse was designed to explode after penetration, not on impact. The shell would punch through armor plate, travel into the ship, then explode inside where it would cause maximum damage. The ballistic trajectory was carefully calculated. The shells left Washington's guns at 45 degrees elevation. They arced upward to a peak height of about 20,000 feet, then descended at a steep angle toward the target. The steep angle meant the shells would penetrate Hiroshima's deck armor, which was thinner than her side armor. The Japanese on Hiroshima had no warning. They couldn't see Washington. Their lookouts were focused forward toward Henderson Field. The first indication they had of danger was when 9 shells arrived. The first salvo hit Hiroshima superstructure and foredeck. 2 shells struck the forward superstructure. Both exploded. The bridge area was smashed. The rangefinder on top of the bridge tower was destroyed. Fire control equipment was wrecked. Communications lines were cut. Electrical cables were severed. Fires started immediately as fuel lines and hydraulic lines ruptured. Hiroshima's captain, Sanji Iwabuchi, was on the bridge when the shells hit. He was knocked down by the concussion but survived. Most of the bridge crew was killed or wounded. Iwabuchi got to his feet and tried to assess the damage. Smoke filled the bridge. Electrical power flickered. Communications to other parts of the ship were cut. He couldn't determine where the firing was coming from. He ordered return fire, but wasn't sure what target to fire at. The gun crews could see muzzle flashes off to the south, but the range was unknown. Washington's gun crews were already reloading. The hydraulic rammers pushed new shells into the breeches. Each shell was mechanically lifted from the magazine below, brought up through the turret structure, and loaded. Powder bags followed. Each gun required 6 powder bags. The breeches closed and locked automatically. The entire loading cycle took about 30 seconds. The second salvo was ready to fire. The fire control solution had been updated based on the latest radar ranging. Washington. Fired again at 01030. This salvo hit Hiroshima forward and amidships. One shell penetrated the armored deck near turret number 1, the forwardmost turret. The shell went through the deck and exploded in a compartment just above the forward magazines. The explosion caused fires and flooding. Damage control parties immediately flooded the magazines to prevent detonation. This saved the ship from catastrophic explosion, but it also disabled turret number 1. With the magazine flooded, the turret couldn't be supplied with ammunition. Another shell hit the forward superstructure and destroyed the backup fire control position. A third shell hit the foremast and brought down the main fire control director. The director fell onto the deck, crushing men below. Hirošima's main battery fire control was now effectively destroyed. Hiroshima tried desperately to return fire. Her aft turrets 3 and 4, were still operational. The local gun captains in those turrets could see muzzle flashes from Washington's guns. They trained their turrets toward the flashes and fired. Hiroshima got off several salvos of 14-inch shells at Washington, but without working fire control systems and without radar, the Japanese gunners had no accurate range. They estimated Washington was about 10,000 yards away based on the brightness of the muzzle flashes. They were close. Washington was actually at 8,600 yards, but close wasn't good enough. The Japanese shells flew toward where Hiroshima's gunners thought Washington was. The shells passed over Washington's masts, missing by perhaps 200 feet. One witness on Washington said, "They must have been mighty close, but close doesn't count." Washington's third salvo fired at 0101. All 9 guns again. This salvo concentrated amidships. 3 shells hit Hiroshima's machinery spaces. 1 shell penetrated the side armor and exploded in the forward engine room. The explosion was devastating. Boilers were ruptured. Steam lines burst. Turbines were damaged. The engineering crew was killed or driven out by superheated steam. Another shell hit near the after engine room with similar results. Hiroshima started losing power. Her speed dropped from 20 knots to 15, then to 10. The ship was dying. The fourth salvo fired at 010130. 2 more penetrating hits amidships and aft. 1 shell went through the deck and exploded in a machinery space near the steering gear. The hydraulic lines that powered the steering were destroyed. Hiroshima lost steering control. The ship began turning slowly in a point circle, unable to control her direction. Another shell destroyed the hydraulic pumps that powered the training mechanism for turrets 3 and 4. Hiroshima's aft main battery was now useless. The turrets couldn't be trained or elevated. The ship had lost all main battery capability. The fire control teams in Washington's plotting rooms watched the radar return. They could see the target was slowing and appeared to be turning. Something was clearly wrong with the Japanese ship. The fire control solution was updated for the changing target motion. The fifth salvo fired at 0102. 2 more hits. 1 shell exploded in crew berthing spaces on the port side. Over 100 men were killed instantly. The other shell hit the after superstructure and destroyed the emergency steering position. Fires were now burning from bow to stern. Hiroshima was completely ablaze. The sixth salvo fired at 010230. 1 massive hit near the waterline on the starboard side. The top shell penetrated the side armor and exploded in a compartment already damaged by earlier hits. Water poured in through the hole. The flooding was uncontrollable. Hiroshima developed a list to starboard that grew steadily worse. The pumps couldn't keep up with the flooding. More compartments were being deliberately flooded to prevent magazine explosions. The weight of water was dragging the ship down. In 7 minutes, Washington had fired 7,516 inches shells in 9 salvos. At least 9 shells hit Hiroshima in vital areas with devastating effect. Modern analysis of the wreck using sonar surveys suggests 17 to 21 total hits, many below the waterline where they couldn't be observed during the battle. Washington's 5 inches secondary battery also fired throughout the engagement. The 5 inches guns engaged multiple targets, including cruisers and destroyers. Approximately 1,075 inches shells were fired. 17 to 20 hit Hiroshima. These smaller shells couldn't penetrate armor, but they destroyed everything above deck. Gun mounts were knocked out. Searchlights were shattered. Boats and davits were destroyed. The superstructure was riddled with holes. Men caught in the open were killed by fragments. At 0107, 7 minutes after opening fire, Lee ordered ceasefire. Hiroshima was clearly finished. She was dead in the water, burning from multiple fires, listing heavily to starboard, unable to steer or fight. There was no point wasting ammunition on a sinking ship. Washington had other concerns. Japanese destroyers were launching torpedoes. Lee had to maneuver to avoid them. Type 93 torpedoes were already in the water. Every Japanese destroyer had launched their full loadout when they detected Washington's muzzle flashes. Dozens of torpedoes were running toward Washington's last known position. The torpedoes ran at 48 knots, with almost no visible wake. They were nearly impossible to see at brown night. Lee ordered emergency maneuvers. Hard left rudder, increase speed to 25 knots. Then hard right rudder, then left again. Washington zigzagged through iron bottom. Sound at high speed. Lookouts on Washington spotted torpedo wakes crossing ahead of the ship. More wakes. Past astern. Washington was surrounded by torpedoes running in multiple directions, but Lee's constant maneuvering kept the ship clear. The Japanese had aimed at where Washington should have been based on her gun flashes. They couldn't adjust aim without radar. Lee's zigzag pattern meant Washington was never where the torpedoes expected her to be. It was a close call. Several torpedoes passed within a 100 yards, but none hit. Washington maneuvered through the torpedo water and emerged without damage. At 0300 hours, Lee ordered Task Force 64 to withdraw south. The mission was accomplished. Hiroshima was sinking. The Japanese bombardment had been stopped. Henderson Field was safe. There was no reason to stay and risk further damage. Lee formed up with the damaged South Dakota and surviving destroyers and headed back toward Guadalcanal. Behind Washington, Hiroshima was in her death throes. Japanese destroyers Esagumo and Terazuki came alongside to evacuate survivors. Captain Iwabuchi and most of the crew abandoned ship. Over 2,000 men were rescued. Light cruiser Nagara attempted to take Hiroshima in tow, but the damage was too severe. The battleship was flooding in multiple compartments. The list to starboard reached 18 degrees and kept increasing. The ship was settling by the bow. At 0325 hours, 3 hours and 25 minutes after Washington's first salvo, Hiroshima capsized and sank. 212 men went down with her. The ship sank about 7:12 mi northwest of Savo Island in water over 2,000 feet deep. USS Washington had accomplished what no other American battleship would achieve during World War II. She had defeated an enemy battleship in a one-on-one surface engagement. More importantly, she had proven that radar could dominate naval Combat. Washington had tracked Kirishima on radar for over 20 minutes while remaining invisible to Japanese lookouts. Washington had fired 9 salvos of calculated fire without visual spotting and achieved devastating accuracy. The engagement demonstrated that electronics had become more important than eyesight in naval warfare, but understanding the full significance of the victory took time. The official Navy action reports focused on Admiral Lee's tactical skill and crew training. Captain Davis wrote in his report that radar was critical, but many readers interpreted this as radar being helpful rather than decisive. Senior officers still thought of naval combat in terms of visual range gunfire and torpedo attacks. The idea that ships could fight entirely by electronics was difficult for men trained in traditional methods to fully accept. Captain Davis understood what had happened. In his action report, he made a statement that would prove prophetic. Radar has forced the captain or officer in tactical command to base a greater part of his actions on what he is told rather than what he can see. This was revolutionary. For centuries, naval commanders had operated by looking at the enemy and making decisions based on visual information. They could see the enemy formation. They could see where shells were landing. They could see damage on enemy ships. Now they would sit inside ships and make decisions based on electronic displays showing dots and numbers. The nature of naval command had fundamentally changed. But changing command required more than technology. It required new doctrine, new training, and new organizational structures. In November 1942, these didn't exist. They were created in the months after Guadalcanal based on lessons from Washington's victory. The Navy began developing formal procedures for organizing radar information. Before Guadalcanal, radar operators worked in scattered locations around ships with no standardized procedures. After Guadalcanal, the Navy began centralizing radar displays, plotting tables, and communication systems into dedicated spaces. By January 1943, the Navy formally designated these spaces as combat information centers. Trained personnel staffed the CIC to maintain situation awareness for the commanding officer. The CIC concept was developed directly from lessons learned at Guadalcanal. If Washington had possessed a fully developed CIC in November 1942, the battle might have been even more one-sided. As it was, Washington's crews improvised effective procedures that became the foundation for future CIC doctrine. The Navy also created formal training programs for radar operators and CIC personnel. Before Guadalcanal, radar training was minimal and inconsistent. After Guadalcanal, the Navy established schools teaching operators how to interpret radar returns, track multiple targets, maintain plots, and communicate effectively with bridge officers and weapons stations. Officers received training in how to command using radar data as their primary information source. The curriculum emphasized that radar wasn't a backup to visual systems. It was the primary sensor, especially at night. Tactical doctrine changed fundamentally. Before Guadalcanal, formations were designed around visual signaling and optical fire control. Ships operated in columns or lines where each ship could see the next. Flag signals controlled maneuvers. After Guadalcanal, formations were designed around radar coverage. Ships with superior radar systems were positioned where they could track the most contacts. Multiple ships coordinated fire using radar data shared by radio. Task force commanders were required to use ships with the best radar as flagships regardless of which ship was most powerful. This represented a complete inversion of traditional doctrine. The impact became clear within a year. In November 1942, American forces were barely holding their own in night battles against the Japanese. By November 1943, Japanese ships avoided night engagements unless they had overwhelming numerical superiority. 3 night surface actions in the second half of 1943 demonstrated American dominance. At Vela Gulf in August, American destroyers using radar detected Japanese destroyers at long range, maneuvered into position and destroyed 3 Japanese destroyers with radar-directed torpedo attacks before the Japanese knew American ships were present. At Empress Augusta Bay in November, American cruisers and destroyers defeated a Japanese force using radar-directed gunfire at Cape St. George. In November, American destroyers intercepted and destroyed 3 Japanese destroyers in a night action entirely controlled by radar. American forces took minimal damage in all 3 engagements. Night combat had become an American advantage. The Japanese tried desperately to adapt. They examined wreckage from sunken American ships and found radar equipment. They understood the principle of using radio waves to detect ships, but they were years behind in development. Japanese radar in 1943 was roughly equivalent to American radar. In 1941, the equipment was less reliable, had shorter range, and lacked the sophisticated displays that American systems featured. By the time Japan developed working surface search radar comparable to the American SG, it was 1945 and the war was nearly over. Even then, Japanese radar was fitted to only a handful of ships. Japanese commanders also struggled with the psychological impact of fighting an enemy they couldn't see. For 2 years, Japanese destroyer and cruiser captains had dominated night battles through superior training and aggressive tactics. They developed confidence that bordered on arrogance. Japanese night fighting doctrine was taught throughout the Navy as the gold standard. Now they were being beaten consistently by ships they couldn't see, firing from ranges where visual spotting was impossible. The confidence built over 20 years of training evaporated. Captains who had been aggressive became cautious. Units that had pressed attacks began withdrawing when radar-equipped American ships appeared. The psychological shift was as important as the tactical shift. Several experienced Japanese commanders were killed in late 1942 and throughout 1943 trying tactics that had worked perfectly before Guadalcanal. They closed to short range for torpedo attacks and were destroyed by radar directed gunfire before they could launch. They tried to use searchlights to illuminate targets and were hit by ships firing from beyond searchlight range. They attempted to evade by maneuvering at high speed and were tracked continuously by radar. The fundamental problem was that they were fighting an enemy using a technology they couldn't detect and couldn't counter. It's impossible to develop effective tactics against a capability you don't understand. Admiral Lee understood this completely. After the battle, he wrote a letter to Admiral Holley that demonstrated remarkable insight and humility. Lee stated that American superiority at Guadalcanal was due almost entirely to radar. He wrote explicitly, "We realized then, and it should not be forgotten now, that our entire superiority was due almost entirely to our possession of radar. Certainly, we have no edge on the Japs in experience, skill, training, or performance of personnel." Lee was absolutely correct. Japanese crews were superbly trained. Japanese officers had more combat experience. Japanese doctrine was more developed. Japanese equipment, especially torpedoes, was in many ways superior. The only American advantage was radar, and that one advantage was decisive. Lee never received full public credit for this insight during his lifetime. He was awarded the Navy Cross for his actions at Guadalcanal. The citation praised his leadership and tactical skill. He Was promoted to vice admiral in 1944 and given command of all fast battleships in the Pacific Fleet. As Commander Battleship's Pacific Fleet, he participated in every major campaign from 1943 through 1945. But most histories of Guadalcanal focused on the desperate surface actions of November 12 and 13, where Admirals Callahan and Scott died leading close-range attacks against overwhelming odds. Those actions had clear heroes and dramatic sacrifice. Lee's victory on November 14 and 15 received less attention because it appeared too easy. Washington suffered 0 casualties. She wasn't even scratched. It didn't look like the same kind of heroic struggle. But Lee's victory was actually harder than it appeared. The decision to trust radar completely was radical in November 1942. Most admirals considered radar interesting but unproven. They'd been trained in an era when visual spotting and optical instruments were the only reliable methods. Radar challenged everything they'd learned. Lee bet his entire force on technology that others viewed skeptically. If the radar had failed, if the data had been wrong, if the fire control solutions had been off by even a few degrees, Washington would have sailed blind into a superior Japanese force and been destroyed. The consequences of failure would have been catastrophic. Henderson Field would have been destroyed. Guadalcanal would have been lost. The entire Pacific offensive would have stalled. Lee's genius was understanding that radar was more reliable than human vision in darkness, and then having the courage to act on that understanding. That understanding came from years of study. Lee had spent 3 years as a director of fleet training studying gunnery systems. He'd worked with engineers developing radar equipment. He'd read British reports on radar use in the Atlantic. He'd attended technical briefings. He'd trained his crews extensively. He knew the capabilities and limitations of radar better than any flag officer in the Navy. When the moment came, he trusted his knowledge over conventional wisdom. That kind of leadership is rare in any era. USS Washington remained in service for the duration of the war. She participated in nearly every major Pacific campaign from 1943 onward. She screened fast carriers at the Battle of the Philippine Sea in June 1944, where American carrier aircraft destroyed hundreds of Japanese planes in what became known as the Great Marianas Turkey Shoot. She was present at the Battle of Lee Gulf in October 1944, though she didn't engage in surface combat. She bombarded Japanese positions during the assaults on Iwo Jima in February 1945 and Okinawa in April and May 1945. She was present at the Japanese surrender ceremony in Tokyo Bay on September 2, 1945. After the war, Washington was used to transport soldiers home as part of Operation Magic Carpet. She made 2 trips across the Atlantic in November and December 1945, carrying over 1,600 soldiers from Europe to the United States. She was decommissioned on June 27, 1947 at the New York Navy Yard and placed in the Atlantic Reserve Fleet. She remained in reserve for 13 years while the Navy decided what to do with World War II-era battleships. By 1960, it was clear that battleships had no place in modern naval warfare. Aircraft carriers and guided missiles had made gun-armed surface ships obsolete except for shore bombardment. Washington was stricken from the Naval Vessel Register on June 1, 1960. She was sold for scrap on May 24, 1961, to Lippitt Division of Lura Brothers Company in New York. The ship was towed to the scrapyard and gradually taken apart. Her 16-inch guns were sliced apart with cutting torches. Her armor plating was removed and smelted down. Her superstructure was dismantled section by section. By the end of 1961, USS Washington had vanished except as scrap metal. A few artifacts were rescued before demolition. The ship's bell was kept. The ship's wheel was preserved. Several commemorative plaques and deck fittings survived. These items today reside in various naval museums and archives. Captain Glenn Benson Davis remained in the Navy after the war. He was promoted to Rear Admiral and commanded Battleship Division 8 during the Marianas Campaign in 1944. He continued rising in rank and eventually became Vice Admiral. He served as Commandant of the Washington Navy Yard from 1950 to 1952 and Commandant of the 6th Naval District in Charleston, South Carolina. He retired from the Navy in 1954 after 43 years of service. Davis died on September 9, 1984, in Bethesda, Maryland, at age 92. His contributions to radar doctrine and his partnership with Admiral Lee were noted by naval historians, though he remained modest about his part. In interviews late in life, Davis consistently credited Lee's vision and the crew's training for Washington's success. Admiral Willis Augustus Lee never saw the war's end. On August 25, 1945, 10 days after Japan surrendered, Lee suffered a severe heart attack. He was being ferried in a motor launch across Casco Bay from his shore headquarters to his flagship, USS Wyoming. Anchored in Portland Harbor, Wyoming never saw him board. Lee collapsed in the boat and died before reaching her. He was 57. The cause was acute coronary thrombosis, essentially a massive heart attack. 3 years of relentless stress commanding battleship forces in combat had taken a heavy toll. Lee had been engaged in combat operations almost non-stop from August 1942 to August 1945. He had commanded during some of the most intense naval battles of the war. The physical and psychological strain had been overwhelming. Lee was buried with full military honors at Arlington National Cemetery in Virginia. His grave is marked by a simple white marble headstone. The inscription lists his name, his rank of vice admiral, and his birth and death dates. It notes his 7 Olympic medals. It does not mention Guadalcanal. It does not mention that he proved radar could revolutionize naval warfare. It does not say that his mastery of technology gave the United States a decisive edge in the Pacific. Lee would likely have preferred it that way. He was never interested in glory or fame. He cared about solving problems and winning battles. The engagement between USS Washington and Kirishima lasted just 7 minutes from first salvo to ceasefire. During that time, Washington fired 75 rounds of 16-inch ammunition and 107 rounds of 5-inch shells. The 16-inch projectiles alone weighed over 100 tons in total. The propellant charges added another 70 tons. The total ammunition expenditure was about $150,000 in 1942 dollars, roughly $2.5 million today. The cost was trivial compared to the strategic importance of the victory. Washington's triumph saved Henderson Field from destruction. Japanese forces never again attempted to eliminate the airfield with naval gunfire. Without Henderson Field, American forces on Guadalcanal could not have maintained air superiority. Without air superiority, resupplying and reinforcing the Marines would have been nearly impossible. Japanese planes and ships would have controlled the waters around Guadalcanal. The campaign might well have been lost. Had Guadalcanal fallen, the entire American offensive strategy would have been imperiled. The island-hopping plan depended on establishing forward bases. If the first major attempt collapsed, it could have taken months or years to rebuild the forces required to try again. But the greater long-term consequence was proving that radar could dominate surface combat. Before November 15, 1942, radar was viewed as experimental equipment that might help under certain circumstances. After that night, radar was recognized as the foundation of modern naval warfare. Every navy worldwide began urgent radar development. Ships were retrofitted with radar. New ships were designed from the keel up with radar as a primary sensor. Tactics and doctrine were rewritten around radar's capabilities. The age of visual range combat ended. The era of electronic warfare began. The shift happened astonishingly quickly. In January 1942, fewer than 100 American warships carried radar of any kind. By January 1945, nearly every American ship had multiple radar systems: fire control radar, air search radar, surface search radar, identification gear. Warships carried half a dozen radar sets, each tailored to a specific task. Electronics became as essential as the guns themselves. Some historians argue radar was the single most important naval technology of World War II, more crucial than aircraft carriers, submarines, or any individual weapon. The lesson from Washington's victory is not merely about technology, it is about leadership willing to trust new technology when conventional wisdom says not to. Admiral Lee had decades of experience in an era when battleships fought using visual spotting and optical rangefinders. Every instinct formed in 34 years of service should have pushed him toward caution. His career had been built on mastering traditional gunnery. He was arguably the finest gunnery expert in the Navy. He could easily have relied on established methods. Instead, Lee set aside tradition completely. He committed fully to radar because he had done the intellectual work to understand it. He studied the engineering principles. He evaluated combat reports. He trained his crews thoroughly. He tested the systems in drills. He knew radar would work because he had verified it himself. When the moment came, in total darkness, with destroyers sinking and another battleship disabled and a superior Japanese force closing in, Lee trusted his radar operators and fire control crews to do something unprecedented. He ordered Washington to fire at a target no one could see, using data from electronics most officers still doubted. The crew did not fail him. The radar tracked flawlessly. The fire control computer calculated accurately. The guns fired with precision. 9 salvos in 7 minutes destroyed a Japanese battleship. 0 American casualties. The victory validated everything Lee believed about radar. It proved electronics could be more dependable than human senses. It showed that properly integrated technology could overcome inferior numbers and disadvantageous conditions. Most importantly, it demonstrated that innovation thrives when leaders understand new capabilities deeply enough to trust them wholeheartedly. That kind of leadership is rare. Most commanders rely on routine. They trust proven methods. They avoid risk by repeating what has always worked. Innovation demands the opposite. It requires risk. It requires embracing untested ideas. It requires relying on technology that has not yet earned its place through experience. Admiral Lee did all of this. He organized his ship around technology many considered unproven. He trained his crew to fight in a manner no navy had ever attempted. He committed his entire force to a battle plan that relied on radar functioning perfectly, and it did. The result transformed naval warfare. Night combat, a Japanese advantage for 2 years, became an American strength almost overnight. The technology Lee trusted in November 1942 became the bedrock of every navy on Earth. The radar displays and fire control computers that seemed revolutionary in 1942 evolved into the modern combat systems aboard warships today. The lessons Lee demonstrated that electronics can outperform human senses, and that technology properly applied can defeat larger forces, remain true 8 decades later. USS Washington's victory deserves to be remembered not just for what happened that night, but for what it symbolized: a commander willing to embrace new technology, a crew trained to wield it, a tactical triumph that reshaped strategic reality, and a powerful demonstration that innovation succeeds when knowledge replaces assumption, when study replaces habit, and when the courage to act differently achieves results impossible under old methods.